Hello, pre-calculus students. Today we're going to start a chapter on exponential and logarithmic functions. Everybody panics about logarithms. Pay attention. You're going to get this. I will explain it to you very well. Today we're going to start with exponential functions and their graphs. So let's start with a review of transformations. Remember, if you multiply a function by a constant a, that causes a vertical stretch to the parent graph f of x. If you multiply x times a, you're going through the x's a times as fast, so it will take 1/8 as long. If you're going through your x's 4 times as fast, it will take 1/4 as long to get to a specific y value. So what you're actually doing is compressing the graph horizontally. And of course, if a is between 0 and 1, you're like going through half as fast, it will stretch it. If we want to reflect something over the y-axis or the x-axis, we make these changes to our parent graph, and these for translations. All of this should be reviewed. So we're going to look at exponential functions. Exponential functions are functions of the form y equals a to the x, where a is a number greater than 0, but not equal to 1. I'll show you in a moment why we want a to be positive. And it can't be 1 because you'd have 1 to the x. 1 to the x is just 1. And you would have a horizontal line, and that's not an exponential function. The reason we want our a values, our base, sometimes people call it b to the x, for b for base. The reason we want our base to be positive is because, let's see, if we have -2 raised to the x power. Well, if x is 0, it's up here. If x is 1, it's -2 to the first, it's down here. At 2, you have -2 quantity squared is 4. -2 quantity cubed is -8. What would your graph be doing? Well, I just showed you the whole numbers. Now imagine for every little number in between here, like that, your graph's going to go up, down, up, down, up, down, up, down. And what you may not know, and don't write this down, this is just for your edification. We can prove that between every 2 rational numbers, there's an irrational number, and between every 2 irrational numbers is a rational number. And so you have this infinite number of numbers, and we have to figure out, well, would it be a positive or a negative? So our graph's going to be doing crazy things, and it may not even be continuous at that point. So we're just not even going to worry about negative bases. So let's take our graph, our parent graph of y equals 2 to the x. Please write down these transformations, then we'll take a look at what each of those graphs look like. Let me correct my grammar. What each of those graphs looks like. Okay, you could have paused. So let's take a look at those graphs. I've graphed them using the program called Graph. I think I've even linked to it in Google Classroom. So here's y equals 2 to the x. You can see it's got this horizontal asymptote of y equals 0. As x goes to -infinity, y goes to 0. At 0, it's 2 to the 1. At 1, it's 2 to the first. At 2, it's 2 to the second, etc. Let's see if I can get some axes in here real quick. There, make it a little easier. So now to show you what we mean by stretching vertically, we're going to go 3 times 2 to the x. You can see all the y values are now 3 times as high. Now we're going to flip it over the x-axis by making that 3 into a negative 3. So there's y equals 3 to the 3 times 2 to the x. Here's negative 3 times 2 to the x. Then I'm going to translate this, the yellow curve, 4 units to the left, and I'm sorry, 4 units to the right, and 2 units up. So you can see that this point here at negative 3, 0, got translated 4 units to the right, 3 units up. I'm sorry, 2 units up. So our vertical asymptote, our horizontal asymptote now, instead of y equals 0, is now y equals 2. So if we have y equals 2 to the x, we call that exponential growth because a, our base, is greater than 1. 2 is greater than 1. So as x gets bigger, 2 to that power is getting bigger. Now here we have 2 to the negative x. You could think of that as reflecting it over the y-axis, in which case it gives you exactly this graph. Or you could use some of your rules of exponents, which you can't see right now because I'm not sharing my screen with you. There we go. So here's 2 to the x, exponential growth. Here's 2 to the negative x, which is reflected over the y-axis. Another way you could think of that is negative x is negative 1 times x. You know, when you raise a power to a power, you multiply the exponents. And 2 to the negative 1 is 1/2. So in this case, you could think of our base is between 0 and 1 because it's 1/2. So as x gets bigger and bigger and bigger, 1/2 to the x, you keep multiplying by 1/2, 1/2, 1/2, x gets smaller, smaller, smaller. And we call this, when your base is between 0 and 1, we call that exponential decay. So just to kind of reiterate, your bases must be greater than 0, but not equal to 1. And if your base is greater than 1, it's exponential growth. And if it's between 0 and 1, it's exponential decay. The usual bases that we use in math and science are base 10 and base E. E is 2.718, and it goes on forever. It's a transcendental number like pi is. It's actually equal to this limit. Try it. Put n equals 100 in and see what you get. Put n equals 1,000 in, see what you get. N equals 10,000, see what you get. And you'll see you're getting closer to a number that starts with 2.718. So what's a common place where we use exponential functions? Compound interest in the bank. Common rate that you'll get today on a savings account or a checking account is 1/100th of 1%. If you get a certificate of deposit, maybe you can find one that'll pay 1% per year. So compound interest, what it does is it takes your interest rate, how much interest you get per year, and it divides it by how many times you're going to get interest. Usually a bank pays you interest every day of the year. So you divide that interest rate by 365, and then you'd get it 365 times a year. So n is the number of times per year, t is the number of years, so n times t is the total number of compoundings, how many times you get interest. So just as an example, Here's the formula for compound interest. If you put $10,000 in the bank at 1% interest, that you get interest every day of the year for 5 years. You might say, well, that's 5%. Well, that would be simple interest, but you're getting interest every day. So on the first day, you get interest on that $10,000. On the second day, you get interest on that $10,000 plus interest on that little bit of interest you got the first day, and so on. So you keep getting interest on your interest as well. So instead of just being 1% for 5 years, instead of that being 5% or $500, compound interest would make it worth this much. So if we're looking at exponential functions, what are their asymptotes? Exponential functions have horizontal asymptotes, as we've already seen. And another thing, exponential functions are one-to-one. That means they are constantly increasing or constantly decreasing. So for each x, there is exactly one y, and for each y, there is exactly one x. It's one-to-one. Now, just to show you a little bit about those other graphs or those other bases I mentioned. Here we go. Share my screen with you this time. Here we are at y equals 2 to the x. We're going to do e to the x next. Now, e is bigger than 2, so it should be steeper. So it's shallower out here, but then it gets steeper out here. And then 10 to the x is, again, shallower still out here, but it gets much steeper out here. But you'll notice all three of them go through the point 0, 1. Okay, need my next set of slides. When we solve exponential equations, the first thing we want to do is see if we can solve it by getting both sides of the equal sign to be written with the same base. So I've got 10 to the x here, I've got 100 to the x minus 5 power here. You just have to notice that 100 is a power of 10, so I can write them both with the same base. Now that's 10 to the second to the x minus 5. We know from our rules of exponents that you can raise a power to a power by multiplying the exponents together. Now, since those exponentials are one-to-one, 10 to this power equals 10 to this power, well, this power must equal this power. What we're really doing here is we're taking the log base 10 of both sides, but not tell anyone yet. We're just going to set the exponents equal for right now, given that they have the same base. And then you solve for x. Substitute in 10 to the 10th power is 1 with 10 zeros. 100 to the 5th power is, let's see, that's 10 squared to the, yep, 10 to the 10th, 1 with 10 zeros. That's done. So x equals 10. Have to get both of them with the same base. You don't have to. Once we do logarithms, we could solve this problem even if that were 28 to the x. We'd be able to solve this for x. But for right now, we want to try it with getting both sides with the same base if we can. And sure enough, this is a base of 3. We can rewrite this side as a base of 3 because 3 to the 3rd power is 27. Again, because they're 1 to 1, this exponent must equal this exponent. But what we're really doing is taking the log base 3 of both sides. Don't tell anyone. Set the two exponents equal to each other and solve. So is 3 to the 3/2 equal to 27 to the 1/2 power? Well, there's 3 to the 3/2, 27 to the 1/2. Remember that if you raise a number to a fractional power, the numerator is the power, the denominator is the root. So you can call that 27 to the 1/2. So it's the square root of 27 on both sides. These already have the same base, so we're just going to set the exponents equal to each other. What we're really doing is taking the log base e, or the natural log of both sides. But don't tell anyone yet. Set the exponents equal to each other and solve. Substitute back into the original equation to check your answer. Now in this problem, I might ask, is this function increasing or decreasing? Well, you say e is bigger than 1, but what about that 0.17? So if it's increasing, our base has to be greater than 1. If it's decreasing, our base is between 0 and 1. What is e to the 0.17? Well, you can see that we can rewrite that as e to the 0.17 power raised to the x. And e to the 0.17 is this. So sure enough, this is an increasing function. If it were e to the negative 0.17x, well, e to the negative 0.17 would be a number between 0 and 1. That's what would make it decreasing. Let's go back to our compound interest formula. This is discrete compound interest. You get interest n times per year. This is continuous. And what we find, though, is that, well, we won't derive it, but we'll kind of get a feel for it in a minute. I'm not convinced there's any place in the world where we deal with continuous compound interest. I think that's just a mathematical thing, kind of like simple interest. But let's just start here. If we put in $10,000, the interest rate is 2%, we do it for 1 year. If you get interest 1 time per year, that is actually simple interest, and you get $10,200. What if you get interest quarterly, 4 times per year? Well, you can see that our interest went from $200 to $201.50. What if you get interest every month? Went up again. What if you got interest every day? It went up again. So you can see the more times we compound, the higher your interest is. So does that mean if we had an infinite number of compoundings, in other words, continuously, if we had an infinite number of compoundings, would our interest go up infinitely? And of course, the answer is no, because I already gave you the formula. A equals PE to the RT, so that's the PERT formula. And if that means that if you got interest an infinite number of times, continuous compounding, this would be the maximum amount of interest you would receive on $10,000 at 2% interest per year. You'll notice it ends up being to the nearest cent, it ends up being the same as if you got compounded daily. So what I want you to get out of this lesson is the concept of what an exponential function is, what causes an exponential function to be increasing, what causes an exponential function to be decreasing. And Eventually, you're going to need to know those two formulas for compound interest, so start committing them to memory. Other than that, have a great day.